you do this one of two ways. One way is to factor a 2 out of the numerator. So let's do that first. So I could factor a 2 out of the numerator. If I did, the numerator would be 2 times 2 minus the square root of 5. Multiply it back out to check to see if you're correct. Notice 2 times 2 would be 4. Minus 2 times the square root of 5 would give you that other term here. All over 2. Now, since it's 2 times this other factor, you can divide the 2's out, and we end up with 2 minus the square root of 5. And there's the answer in simplest form. Alternatively, you could have done this. We could have gone from here and then written this as 4 over 2 minus 2 times the square root of 5 over 2. Since there are 2 terms in the numerator, we could just say each term over 2 and then subtract those two. 4 over 2 minus 2 times the square root of 5 over 2. 4 over 2 reduces to 2. These 2's divide out again. It's just 2 over 2 is 1. So we get minus 1 times the square root of 5 or square root of 5. Same answer. Okay? I think we did that one in class, but there it is. What else we got here? In the book on page 637, I can't really show it to you here because of how I set this up. I can't move things around a whole lot. There's a, it says, simplifying the nth root of a to the n. They have this. Remember, this is an nth power, this is an nth root. They undo each other. But they have this on page 637. I can lean over here and look at it. Let me see. It says the nth root of a to the n equals the absolute value of a if n is greater than or equal to 2 and is even. In other words, if n is equal to 2 or 4 or 6, etc. Now, we said when we do problems, we're not going to worry about that. The problem's going to say, don't worry about that. Don't worry about that absolute value. So we're just going to write, even though it's incorrect, unless you know that a is 0 or positive, and I explain why in class, so I'm not going to do it here, but we're just going to write the nth root of a to the nth is a, which I've been doing already in the problems we've talked about. I'm not going to worry about writing the absolute value, and you don't have to worry about it either. You do have to be concerned about that in other, maybe another class or different types of problems, but we're just learning how to simplify, and we're not going to worry about that absolute value. On the other hand, the nth root of a to the n is a if the n is an odd number. Now remember, n must be 2 or an integer, and it must be 2 or greater. But if it's 3 or 5 or 7, if it's like that, you don't even worry about the absolute value anyway. It wouldn't even matter. And we discussed why that was true in class. I showed you that, so you can look at your notes there and see why that's true. Okay, let me see what else is here. Okay, they have a whole bunch of examples like we just did. Here's another one. Let's look at this example. Suppose it says multiply and simplify, or just simplify maybe. And we have square root of 3 times the square root of 15. I'm actually choosing this problem right out of the book. It's example 7 on page, what is that, 638. Now, we did a problem like this a minute ago, if you recall. I don't know where I put it. Well, I'm not going to worry about it. But we did one similar to this. And we said, using the property, since it's 2 radicals multiplied together with the same index, I can write it as one radical again, which I wish to do if it's going to be in simplest form. And I can multiply the 3 and the 15 together. And that's the square root of 45. And see, neither one of these simplifies in either one of these factors. 3 is prime, and 15 is 3 times 5. There's no perfect square in there. But because 15 is 3 times 5, when I multiply these together, I'm going to get a 3 times 3, 9, which is a perfect square. So if I multiplied the 3 and 15, I can write it as square root of 45. I went to the largest perfect square that divides 45, which is 9. So I'll write the 45 as 9 times 5. Use the property. Write it as the square root of 9 times the square root of 5. Square root of 9 is 3. So we end up with 3 times the square root of 5. There it is in simplest form. I could have, at this point, instead of multiplying and getting 45, I could have written this as square root of 3 times 15, which I'll write as 3 times 5. And then I'll write it as square root in factored form, square root of 3 squared times 5. and then do that stuff we did just a moment ago with the exponents. Oh, look, the index is 2. Here's an exponent of 2 or greater, therefore there's a perfect square in there. So I'll write this as square root of 3 squared times the square root of 5. 5 to the first power, no perfect square in there. So this is the perfect square part. Factor it like that. And then square root of 3 squared is 3. Square root of 5. 5 is prime. There's no perfect square that divides it though, but write it like that again. Simplest form. Here's another example. I'm stealing it from the book again on the same page. We have 3 times the cube root of 4x times the cube root of 2x to the 4th Oops. Cube root of 2x to the 4th. I don't know what I'm doing here. Okay, cube root of 2x to the 4th. Notice they're both cube roots. Therefore, I can use the product property and multiply the two radicands together and write it as one cube root. So I can write it as the radicand is 4x times the 2x to the 4th, which becomes 3 times the cube root. Don't forget to write that little index. 4 times 2 is 8, or you can write it as 2 cubed. And then x times x to the 4th is x to the 5th. Now I want to try to simplify the radical part. Since it's a cube root, I'm looking for perfect cubes that divide 8x to the 5th. 8 is a perfect cube. So I'll rewrite this as the cube root of 8. And then x to the 5th, 5, the exponent, is greater than or equal to 3. There's a perfect cube in there. I want the largest exponent, the largest number, greater than or less than or equal to 5, which is divisible by 3, which is 3. So I'll write the x to the 5th as x cubed times x squared. The 8x cubed part is a perfect cube. The x squared is not. It has no perfect cube that divides it. So now I'll use the properties of exponents again and rewrite this as 3 times the cube root of 8x cubed times the cube root of x squared. This first cube root, I can rewrite it, simplify it, and write it without a radical symbol. So we'll end up with 3, that 3, times the cube root of 8, which is just 2. The cube root of x cubed, again, it's, cube root of x cubed is x, but as you just divide 3 into the exponent and get x to the first power, which I don't need to write, the cube root of x squared stays the way it is because that exponent 2 is less than or equal to 3. I can't simplify it. So it's a cube root of x squared. 3 times 2 is 6, so we end up with 6x times the cube root of x squared, and there it is in simplest form. Okay, I guess there's one more there. Let me look at it. We're doing a video, so I probably could, I don't know how my battery's holding up here, but we'll find out. Let's see, here's another one. Simplify this, the cube root of 27, a squared b to the 5th times the 4th root of 6a cubed b to the 6th. Since they're both 4th roots, the index in both of them are the same, the indices are the same, I can write it as one big cube root under one radical symbol, which I'll do. So we'll raise the 4th root. We're going to multiply these together. Let me skip that step if I can this time. So I'm going to multiply these together and put them under one radical. Instead of writing 6 times 27, whatever that is, instead of multiplying it out, which you can if you wish, but you're going to get kind of a big number. So why not just start factoring? Let's write this as 3 cubed and write them in factored form and do it like we do variables. 6 is 2 times 3. So that's still 27 times 6. A squared times a cubed, that's a to the 5th. Add the exponents. B to the 5th times b to the 6th is b to the 11th. Let's rewrite this numerical coefficient here. So we end up with the 4th root of 3 cubed times 3 is 3 to the 4th power times the 2 times a to the 5th times b to the 11th. Okay. Now let's try to simplify it. Look here, if we have since we have the number in a prime factorization form, all we do is look at the exponents. If there's any exponent, 4 or bigger, we can simplify. Oh, here's an exponent of 4. That's a perfect cube. So I'm going to use the property, the product rule. And we'll write 3 to the 4th here, which is a perfect 4th power. 2 is to the 1st power. The exponent is less than 4. If it's 1, 2, or 3, you can't simplify it. So I'm going to write the 2 over here in the non-perfect 4th power factor. A to the 5th, the exponent's 5. That's bigger than or equal to 4. 5 is bigger than or equal to 4. There's a perfect 4th power in there. Again, you choose the largest number less than or equal to 5 that's a multiple of 4, which is 4. So we'll write a to the 5th is a to the 4th times a to the 1st power. 4 and 1 add up to 5. You still have a to the 5th underneath the radical symbol. B to the 11th. 11 is greater than or equal to 11. There's a perfect 4th power in there. Choose the largest number less than or equal to 11, which is a multiple of 4, which is 8. 2 times 4 is 8. So we'll write this as b to the 8th. And then times b to the 3rd. Notice that exponent is less than 4. All these exponents here are less than 4. This factor has no perfect 4th power in it. It's going to stay underneath the radical symbol. So we have these two factors underneath the radical symbol. So let's use the property again, the product rule. So it's the 4th root of 3 to the 4th times a to the 4th times b to the 8th times the 4th root of 2ab cubed. This first radical, this first factor, we can simplify that and write it without a radical symbol because the radicand is a perfect 4th power. Again, taking a 4th root is like dividing 4 into the exponents. So the 4th root of 3 to the 4th is 3. The 4th root of a to the 4th is a, both of them to the 1st power. The 4th root of b to the 8th, 4 goes into 8 two times, so that's b with an exponent of 2. And then times the 4th root, again, don't forget the little index, of 2ab cubed, which can't be simplified any further. There's the answer in simplest form. Okay. Now the other property that we're going to use to help us simplify is the quotient rule. This is the quotient rule. We went over it at the beginning of this video, where I mentioned it. Here it is. The nth root of a over b is the nth root of a over nth root of b, as long as everything is defined. And you can change the left side into the right side or the right side into the left side, just like with this one. Whatever helps you simplify. Okay, let's try a problem. Again, I'm going to steal this one from the book. This is on page 639. It says simplify. This first problem I'm going to look at. The square root of 18 over 25. Notice I look at it and say, 25 is a perfect square. And I can use that quotient rule. The square root of a quotient is the quotient of the square root. So I could write this, if it helps me, and it certainly does, write it as the square root of 18 over the square root of 25. The square root of 25 is 5. Okay, and by the way, let me just take a little detour here just for a minute. Remember, I gave this to you already, but let's go over it again before we go any further. A radical is in simplest form if, and we did number 1 already, we did it in class, if no perfect nth power is a factor of the radicand. That's why when we simplified this one, for example, this problem, or let me, wherever, I don't know, I guess I can use that one. I don't know what I did with the other one I was doing. Well, here it is. Let me use this one instead, just because it's not. When we simplify this one, for example, it is not in simplest form because it doesn't satisfy number 1. There's a perfect nth power, in this case a perfect square, that divides the radicand. So we wrote it as a perfect square times a non-perfect square, the largest perfect square of the there's a factor of the radicand, times the other factor, and then used this property to help us simplify it. Same thing with something simple like this, square root of, or let's do a cube root of 54. 27, this is not in simplest form because there's a perfect cube. The index is 3. See, when it's an nth, if it's an nth root, if any perfect nth power is a factor of the radicand, it's not in simplest form. 27 is a perfect cube. See, the index is 3. So any perfect cubes that divide this, if there are any, it's not in simplest form. So we wrote it as 27 times 2. 27 is a perfect cube. And then, factored it like this using the product rule. The cube root of 27 was 3. And we simplified it. And that makes it satisfy number 1 here. There's no perfect nth power that is a factor of the radicand when we finished all these problems. The other two conditions for perfect to be in simplest form for and you should know this, these three, you should memorize them. There can be no fractions under the radicand. The third one, there are no radicals in the denominator. So if we go back to this problem, notice this is not in the simplest form because there's a fraction underneath the radical symbol. That's number 2. There can be no fractions in the radicand underneath the radical symbol. So we use the properties, one of the properties, the quotient rule, to write it like this. But now there's a radical in the denominator. It doesn't satisfy number 3. However, the square root of 25 is 5. So now number 3 is satisfied. But the square root of 18 is not in simplest form because it doesn't satisfy number 1. 9 is a perfect square, and it divides 18, and we're doing a square root. Remember, the index is 2. So we worry about square roots. Perfect squares dividing 18. So we're going to write the square root of 18 as the square root of 9 times 2. That's the square root of 9 times the square root of 2, all over that 5. And the square root of 9 is 3, so that's 3 times the square root of 2 over 5. Now it satisfies all 3 of these conditions. There's no perfect square that is a factor of the radicand. There's no perfect square that divides 2. 2, in fact, is prime. There's no fraction underneath the radical symbol. 2 is not in fraction form. And there's no radicals in the denominator. So it satisfies all 3. That's an example. Let's look at the next example. This is also from the book. It's the cube root of z, again, simplify, the cube root of 6z cubed over 125. It's not in simplest form. There's a fraction underneath the radical symbol in the radicand. So we can use the property, the quotient property, and write it as a cube root of 6z cubed over the cube root of 125. Now there's no fraction underneath either radical symbol, but there's a radical in the denominator. So it violates that condition for simplest form. However, 125 is 5 cubed. Now everybody knows that, but 125 is 5 cubed. So the cube root of 125 is just 5. So I can put a 5 in the denominator, no radical symbol. And the numerator is a cube root of 6z cubed. So now there's no fraction underneath the radical symbol. It satisfies that condition. There's no radical in the denominator. It satisfies that. This is a 3, by the way. That's supposed to be z cubed there. But it doesn't satisfy number 1. See, it satisfies 2 and 3, no fractions underneath the radical symbol and no radical in the denominator. But it doesn't satisfy number 1 now because there's a perfect cube. Z cubed is a perfect cube, exponent 3, multiple of 3. And it's a factor of the radicand in the numerator. 6, it's 2 times 3. There's no perfect cube divides that. So we'll simplify the numerator some more. Leave the denominator the way it is. So we have the cube root of z cubed, perfect cube, times the 6, not a perfect cube. Write the numerator then as a product, cube root of z cubed times the cube root of z, or 6, I'm sorry, over 5. Cube root of z cubed is z. So we just replace that with z times the cube root of that 6, all over 5, simplest form, which satisfies all 3 conditions now. There's no perfect nth power, in this case perfect cube, that divides 6, the radicand. There's no fraction underneath the radical symbol, and there's no radical in the denominator. It's just a 5 down there. Simplest form. Okay? Whoops. Okay. All right, and okay, I'll look at this last example here. What the heck, we're doing a video, so get plenty of time. Here's another example of the book. 4th root of 10a squared over 81b to the 4th. Simplify. There's a fraction underneath the radical. So let's write it as the 4th root of 10a squared all over the 4th root of 81b to the 4th. Notice I always write the index A lot of students leave that off in the steps. They start writing it like a square root. You don't write an index. If it's a square root, you don't need an index. You can write it if you want, but you don't have to, so we don't write it usually. But any index greater than 2, 3 or 4 or 5, you write it every time. Okay, so now we satisfied one condition. There was a fraction underneath the radical. Now there's not. But now there's a radical in the denominator. But in this case, works out pretty nice. 81 is 3 to the 4th power. 9 times 9, or 3 times 3 times 3 times 3. So the 4th root of 81 is 3. So the 4th root of 81 is 3 because it's a perfect 4th power. 4th root of b to the 4th is b. Look at the exponent of 4. Again, you divide 4 into the exponent and get 1 for the exponent, and then don't write the radical symbol. So we have this. Now there's no fraction underneath the radical. Satisfies that condition. There's no radical in the denominator. That's okay. But what about the numerator? Well, 10 is 2 times 5. There's no perfect 4th power that divides that. A squared, look, the exponent is less than or equal to 4, or less than 4. If it's 4 or bigger, you can simplify it, but it's 2, it's less than 4. There's the answer in the simplest form. You're done. Okay. Here's some more examples, again from the book. I'm not going to pick them all. I'm looking on page 640 now, because we only have, I don't want to, well, anyway, I'm not going to do them all. Let me pick example 9. I'll jump to B, which is a cube root. It says simplify this, -2 times the cube root of 54a over the cube root of 2a to the 4th. Notice this time, instead of having the root of a fraction, we have a fraction where the numerator and denominator both have radicals in them, and they're both the same index. That's important. We'll deal with problems where the index is not the same, but here the indices are the same. So we could approach it like we did these up here. However, when you have one like this, look to see if you write it as one radical, just the cube root of one big radical, because you can change it back. See, I could change this step right here back into this one if I wanted, but it doesn't help me because this doesn't simplify at all. But if I wrote this one as -2 times the cube root of 54a over 2a to the 4th, which I'm allowed to do using the quotient property, I can simplify this, and it may make the problem a lot easier for me. So let's write it like that, because it'll help a lot in this problem. Okay? So we have -2 times the cube root of. Now I'm going to simplify this fraction, because I can divide 2 into 54. Divide 2 into 54. 2 into 54, what's that? It's 27. So 54 over 2 is 27. And a over a to the 4th, this a divides out one of those a's. Or you could say a to the 1 minus 4, a to the -3rd, and then move it down in the denominator. But I'm assuming you know how to simplify this part. A over a to the 4th is 1 over a cubed, but there's an a cubed down in the denominator. Now it looks like one of those problems we just did a minute ago. Now, let's write it as, there's a fraction underneath the radical symbol, not in simplest form. So let's write this as the cube root of 27 over the cube root of a cubed. Now, there's no fraction underneath the radical symbol. Satisfies that condition. But now we have a radical in the denominator. But the cube root of a cubed is a. So I can write the denominator as just a. And the numerator, the cube root of 27, that's not in simplest form because there's a perfect cube that divides 27. 27 is a perfect cube. Cube root of 27 is 3. Times 3. So we get -2 times 3, which is -6 over a, or -6 over a written like that. Okay? I'll do this other example because it looks a little more complicated. How about this one? Let's say we have, let me copy it here. It's a big cube root of -375x squared y over the cube root of 3x to the -1 y to the 7th. cube root of that. Again, this one looks like this. So there might be an advantage of writing it as one big cube root if we can simplify this, and we certainly can. 375 is divisible by 3. Here are x's in the numerator and denominator and y's in both, so let's write it as one big cube root. Using the quotient property, you know, the quotient of nth roots is the nth root of the quotient. I can just write it like this. The cube root of one big fraction like this. And then I can simplify this a lot, which will make the problem easier for me. So I'll write it as a cube root of. Now divide the 3 into the negative 375, which is negative 125. Here's x squared over x to the negative 1. Now, you know, we went over how to deal with negative exponents in a previous section. I'm assuming you know this, but you could write that as x to the 2 minus a negative 1 if you wish. Remember, we can use that property, so it's x cubed. If you wish, you can just move this up here and make that x to the first power and multiply by that x squared, but you're going to get an x cubed. This part right here with the y's, you could say y to the 1 minus 7, which is y to the negative 6, and then move it down in the denominator and get y to the 6. Or you can say this y divides out one of the y factors here, and it leaves me with y to the 6 down in the denominator. So now we have this problem. So we've simplified it a little bit. Now this doesn't satisfy simplest form because there's a fraction underneath the radical symbol. So let's use the quotient property again and write it as the cube root of the numerator over the cube root of the denominator. Now there's a radical in the denominator, and there's a perfect cube that divides the numerator. In fact, this works out really, really nice because, for example, the negative 125, see, negative 5 cubed is negative 125. So the cube root of negative 125 is negative 5, which you should just know. The cube root of x cubed now, I'm assuming you just know that's x. The cube root of y to the 6, see, 6 is a multiple of 3. 3 goes into 6 twice, so that's a y squared down there once I remove the radical symbol. And there's the answer. Okay? Let's take a look at an example like example 10 on page 640. It's a problem. The title says multiplying radicals with unlike indices. So suppose we were to simplify, multiply and simplify, but simplify again the fourth root of 8 times the cube root of the 5. Now those, notice, the indices are not the same. I can't write this as a root and multiply 8 times 5 together. I can't do that because they're not the same index. All the problems we've done so far today, or in this video, you know, we've dealt with radicals that have the same index. They're not the same here. So let's make them the same. To do that, let's write it using fractional exponents. So the fourth root of 8 is 8 to the 1/4 power. We've talked about, you know, how to do that, how to write that with an exponent, but that's what it is. We did that before. You should understand that. The cube root of 5 is 5 to the 1/3. Now remember, when you're writing with a fractional exponent, the denominator tells you the index. This is a fourth root. This 8, you're taking a fourth root of that, and the 5, you're taking a cube root. If I can make the two denominators the same, then I'll have the same root, the same index for both of these radicals if I change it back into radical form. The common denominator is 12. 1/4, I can multiply by 3 over 3 and get 3/12. So I can write the 8 to the 1/4 as 8 to the 3/12. Notice the denominator of 12. 1/3, I can multiply by 4 over 4 to get a denominator of 12. That's 4/12. So the 5 to the 1/3 could be written as 5 to the 4/12. Now, they both have the same denominator, the exponents do. Now, I'll do it a little differently than the book. I'll do it the way the book does too, but I'll do it this way. So we have, this is the 12th root. writing it back in radical form if I wish. It's the 12th root of 8 cubed times this one, 12th root of 5 to the 4th. Remember, when you have a fractional exponent, the denominator is the index and the numerator is the exponent. You can put the exponent on the number or whatever the base is inside the radical or outside, but I put it inside because we want to do that. Just a comment here, 8 is 2 cubed. So 2 cubed cubed, this 8 cubed is 2 cubed cubed, or 2 to the 9th. Notice the exponent is 9. That's less than 12. That means this cannot be simplified. 5 to the 4th, 5's prime. Notice the exponent's 4. That's less than 12. This can't be simplified. So when now I'm going to use the property, the product rule, and write it as 1/12th root. The 12th root of 8 cubed, which is 2 to the 9th if you want to write it that way, times 5 to the 4th. I know this can't be simplified because 8 cubed times 5 to the 4th, if I wrote the 8 cubed as 2 to the 9th, it's 2 to the 9th times 5 to the 4th. There it is, a prime factorization of whatever this number is. No exponent is greater than or equal to 12. So there's no perfect 12th power in there. That's the answer right there. Now, I'm not going to multiply all that out. I'm just going to look in the book. If you multiply this out using a calculator or whatever, it's 320,000. So this is the 12th root of 320,000. And there's the answer. On the other hand, here's another way of doing it. See, from this step right here, from here, you can use properties of exponents too. Let me use a property of exponents to do this problem like the book does. So we can write 8 to the 3/12 as 8 cubed to the 1/12th power. Because you can multiply those exponents to get back to 3/12 times. Same thing with 5 to the 4/12. I can write it as 5 to the 4th to the 1/12th. See, these are both 1/12, so I can use properties of exponents again. Go back and look at them. I don't remember what page you're on, but you can write this as 8 cubed times 5 to the 4th, all to the 1/12th power. Like that. Then 1/12th power means 12th root. So it's a 12th root of 8 cubed times 5 to the 4th, and we're right back to this step or that. But anyway, there's an example. Okay, now that wraps up section 9.4. I think I still got battery life, so let's just move on. And this is a long, boring video probably, but let's go to 9.5, which is called the 9. This is section 9.5 now. Okay, adding, subtracting, and multiplying radicals. When if we had a problem like, let's say, 3x squared plus 5x minus, or let's say plus 2x squared minus